Okay, so let's discuss the first part, the first step, that is domain discretization, right? The domain of a two-dimensional boundary value problem is complex, right? We don't have simple geometries in general. So we should fill our solution region. For example, in this figure, you can see an arbitrary solution domain, right? That is irregular 2D domain. And the first step is filling this solution region using finite elements, right? So we can use different element types, triangular elements, quadrilateral elements. And here in this figure, as you can see, we can fill this solution region using rectangular elements, finite element mesh using rectangular elements. But here, as you can see, we have discretization errors, right? We have discretization errors. If we fill this solution region, this domain, using rectangular elements. So how we can reduce this discretization error? We can use, for example, triangular elements or quadrilateral elements, as you can see here in this figure, right? If we fill the domain using triangular elements, we can reduce the discretization error. Or if we fill the region using quadrilateral elements, we can reduce the discretization error. So this is the first step. And you can see in this figure, triangular elements are quite good. We can fill any desired shape using triangular elements, right? So you can see most of commercial software use the triangular elements, right? That is a generic element type. But quadrilateral elements are also interesting because using lower number of mesh elements, we can fill the region, right? So in what follows, we will solve the benchmark problem both using triangular elements and using quadrilateral elements. So for mesh generation, we should follow these rules, right? That I am going to explain these rules in detail. Actually, for two-dimensional problems or three-dimensional problems, if we are going to get a good answer, we should have a good mesh. We have a parameter named mesh quality, right? And the results depends on the mesh quality. So we should generate a fine mesh, a good mesh, and what is a good mesh, right? So let's discuss these items in detail. Before that, I am going to generate the mesh for a simple structure. Suppose we have a rectangle here, and this is the x-axis, and this is the y-axis. I am going to generate a mesh like this, triangular mesh. Okay, so here I define two parameters. The first one is nx and the second one is ny. I write here number of points along the x-axis is nx from 0 to nx, and this is from 0 to ny, right? So these are my mesh nodes. And for example, this is one element. This is one mesh element, right? I have 9 mesh nodes, and I have 1, 2, 3, 4, 5, 6, 7, 8 triangular elements, right? So how I can define the coordinate of the points and how I can store the mesh data. So let's create a new script and let's save it as our I write here FEM 2D try 1. So CLC clear, close all, save. I'm going to generate this mesh. So as I said, we should define nx. Let's write 3 here. And I define ny. Let's set it also equal to 3. These numbers could be different. And also I define this parameter. Let's say this is the height and this is the width of our solution domain. So I write here width equal to 10 and height equal to 10. The square region, later we can change. Okay. So the first step is finding the coordinate of each mesh point, right? So this is the node index. We can place a node index here 1, 2, 3, 4, 5, 6, 7, 8, 9. So each mesh point should have an index, right? So here I write P, that is my mesh nodes. I allocate, here I write allocate memory for mesh nodes. So I wrote here P, and you know that actually, as you can see here, the number of mesh nodes is nx times ny, right? The number of mesh nodes. So I write here zeros, 2, and nx times ny. Actually, I want to store mesh points like this, something like this. This is one mesh point, is its x coordinate, y coordinate, 2, x coordinate, y coordinate, and so on. So here is P. We allocated the memory. And now I write for I equal to 1 to nx, for j equal to 1 to ny, and end, and I write P1 and index. I write here index equal to 0, and here I write index is equal index plus 1, right? So actually I am going to calculate the x and y coordinates of each mesh point. This point, this point, this point, and so on. So here the x component is changing and y component is constant. So I can write something like this. Let me write here ny and nx. So the value of y coordinate is equal, I can write I minus 1 times, what is the delta y and delta x? I write dx and dy. Here, this is the value of delta x, and here we have the delta y. Here we have a structured mesh. Later, I will explain non-structured mesh, also actually arbitrary mesh. So what is the value of delta x? You know the value of delta x is width divided by nx minus 1, and delta y is h divided by ny minus 1. Okay, so I can write the y coordinate of each of these points is equal I minus 1 times delta y or dy, and the x coordinate is equal to I write j minus 1 times delta x. So when this is nx, this is nx minus 1 times delta x, that is equal to w. So the first coordinate is x, and the second coordinate is y, 2, right? So if I run this code and I write p here, you can see the coordinate of each mesh node. Actually, I can plot it here. I can write here plot p. I write 1 and the first row, then the second row, that is y coordinates of each mesh point, O, and if I run this code, you can see mesh nodes. This is 10, this is 10, we have 9 mesh nodes. Let me set the color to the black and run the code. You can see mesh nodes here, here. So now we should construct the connectivity list, right? The connectivity list. What is the first mesh element that we have here is 1, and this is 2, right? 3, 4, 5, 6, 7, 8. So we calculated the x and y coordinates of each mesh point. Now, what is the total number of mesh elements? The total number of mesh elements is equal 2 times nx minus 1 times ny minus 1, right? This is total number of mesh nodes. When nx is equal to 3, ny is equal to 3, 3 minus 1, 3 minus 1 is 2, 2, 2, that is 8. 8 mesh elements equal to this example. So I write here also the connectivity list. I am going to allocate memory for mesh nodes and connectivity connectivity list. Total elements of connectivity list is zeros, 3, and this is 2 times nx minus 1 times ny minus 1, right? For each mesh element, we should store indices of 3 nodes, right? The first mesh element here, the coordinate of points is the first mesh node, 5 and 4, right? So here we should store this data. Consider that this sequence should be counterclockwise, right? For example, the connectivity list for the first mesh element is 1, 5, and 4. What is the connectivity list for the second mesh element? 1, 2, and 5. 1, 2, and 5. So we should store this data counterclockwise for each mesh element, right? So here I can write the connectivity list also. Actually, I should have a loop also for construction of the connectivity list, right? For the connectivity list. So here also I copy this and I paste it here. I write here index is equal to 0. This is index of points, index of connectivity list, ny minus 1, nx minus 1, and right. So when I iterate over these two for loops, in each iteration I have 2 elements, right? And now I should write something like this. Index 1 and index 2 and index 3 and index 4. I write the code like this for clarity. Later we will write a more advanced course that running time is much more lower, right? So this is just for clarity of understanding the procedure. So I am going to consider this as index 1, and this has index 2, this has index 4, and index 5. So index 1 is equal, here I can write something like this. I can write I. So let me write here n x, and here let's write n, ny, nx. So this is j, and this is j plus 1. This is j plus I minus 1 times n x. Actually, in each row we have nx elements, right? So when the index of this point is 1 and index of this point is 2, index of this point is equal to 4, or actually 1 plus I minus 1 times nx, right? So actually I, right? So let me clear this. This is much more better. Let me draw it again. This is the first element. This is second element. This is index of 1, index point 2. This is index point 3. And this is index point 4. So this is j from 1 to nx minus 1. Index 2 is j plus 1. Index 3 is equal to, I can write something like this. Index 2 plus I times index x, and this is index I. Index 4 is equal to index 1 plus I times n x. So now here I should add the first mesh node. I write here connectivity list of the first element is equal to the indices are I1, I3, and I4 for first mesh element, and for the second one, I1, I2, I3, I1, I2, I3, right? So this is counterclockwise. 1, 3, 4, and 1, 2, 3 is also counterclockwise. So I write something like this. Index 1, index 3, index 4. This is for the first element. For the second element, I add I1, I2, I3, I1, I2, I3. So let me run the code. This is the connectivity list. And now again, how we can plot the mesh. Actually, I can use the patch function again, like before, patch, faces, and vertices. So because I stored data like this is the connectivity list. In the patch function, I should use the transposed format of these metrics and also mesh points. So I should write here a connectivity list transposed, and for vertices, I write here p transposed. And also I set the color of each element. I write here face color, this property to this color, and I set the edge color to black. So let's run the code. Okay, here I should write hold all. I'm going to hold all of plots. So here you can see the mesh elements. So what is the error? What do you think? In the code here, the index 1 is j. All right. Here I should write I minus 1, and this is index 1 plus this. Right. Even we can write index 3 and index 4. So if I run the code, here we have connectivity list 1, 5, 4, 1, 2, 5, 2, 6, and 12. So the error is here. Actually, index 2 is index 1 plus 1. And this is the index 1, and index 3 is index 2. Here I should write plus nx and plus nx because we have only one level up, right? So this is the mesh, right? We can plot the mesh that we generated for our problem. That is a triangular mesh, a structured triangular mesh that you will see later. That is for our benchmark problem, right? Okay, so you can see the mesh here, right? This mesh, right? Let me show it. 1, 2, 3, 4, 5, and so on. And these are indices of each mesh element. So let's check. Let's check. What if I increase nx to 5, right? And ny to, for example, 7. As you can see, we can increase number of elements and generate a fine mesh by setting of those variables, right? So this is one method for generation of the mesh and storing mesh data, connectivity list, and point coordinates. Okay, so do you have any question?
No, it's clear.
Okay,